Question 3 now is about this compound, and the important thing about it is that it's aromatic still, but crucially it has these two OH groups which are different, because this one is a phenol group because it's directly attached to the aromatic ring. This one is an alcohol group because although it's in the same molecule, it's not directly attached to the aromatic ring. And that has important consequences for the properties, and that's what the first part A is getting at, because one crucial difference, in fact the only crucial difference that you need to learn between phenols and alcohols, is that phenols are acidic and alcohols are not. You absolutely have to know that difference, and that's what this question was all about, because obviously if something is acidic, it can react with sodium hydroxide, acid plus alkali, reacts to form a salt plus water, whereas something that's not acidic will just ignore the sodium hydroxide. And so that's all that's happening here, that this group reacts, this group doesn't, so they'll react just once with sodium hydroxide and give you the salt product, which will now, instead of OH at that position, have O minus Na plus. Be very careful how you draw it. Remember, the bond must go to the oxygen, because that's the one that's attached to the ring. If you write it like this or something, it will get marked wrong, because that makes it look as if the sodium is forming a covalent bond, and that's chemical nonsense. Sodium never forms covalent bonds. So you've got to be careful how you draw these things, otherwise you won't get the marks. So it's got to be O minus Na plus. This part of the molecule, as we said, it's non-acidic OH, so it just stays unreacted. And don't forget the water. Acid plus alkali goes to salt plus water. The part B now brings us on to the TLC question. And the first couple of things it asks are just general things. First of all, the explanation of why things separate out in TLC. So again, it doesn't want lots of experimental detail about how you load the plate and all that kind of stuff. It just wants you to say that the mobile phase is a solvent which dissolves the substances and carries them up the plate, but the stationary phase can adsorb those substances, and that's the key word, not absorb but adsorb with a D. Okay, so the stationary phase tends to adsorb those substances, and crucially the more strongly it adsorbs them, the more they'll be slowed down, so the less far up the plate they'll travel. That's the separation, because different substances adsorb to different extents. Then it asks you to measure the RF value for this spot. And remember, RF is the distance travelled by the spot, and you measure it to the middle of the spot from the start line, like that. So make sure it's to the middle of the spot, and then you measure the distance that the solvent has travelled, starting from the same line, and it's just the ratio. So if this distance is x and this distance is y, then the RF value is x over y, and you should have got 0.17. Measure it as carefully as you can. I mean, obviously you don't have to spend hours on it, but take more than a couple of seconds to make sure you get it from the centre of the spot to the line, because they'll give you a bit of a tolerance but not a massive amount. So about 0.17 you should have got for that one. Okay, so the last question is asking us about the actual experiment which has been analysed through this. So for this you had to really read the question carefully, make sure you understood what was going on. So it tells you, top of the page, that this is the compound that you're starting with, same one that part A was about, and that we're doing a nitration reaction on it. And so what we're going to expect to happen, remember that the phenol OH activates the ring at 2, 4 and 6, but 2 and 6 are blocked, so we're going to expect to get nitration at this position. And what's going on here is that samples have been taken at different times during the reaction, and this is showing us what there is in the mixture at those different times. So sample 1, it tells us, was taken at the start of the reaction, so it hasn't had time to form any products yet. So that one is straightforward. There's only one spot there because there hasn't been time for anything to happen. And so that spot, which is spot A, is just the starting compound, which is this. So you can straight away get an easy mark for just saying that A is that which is the starting compound. Now, as I say, what we expect to happen is that we're going to nitrate at that position. So we're going to expect to form this compound. Okay, same thing, all of this bit of the molecule being unaffected, but now with an NO2 there. Again, be careful when you write the NO2 down, the bond's got to go to the nitrogen. If you write it like that, that's going to get marked wrong, because it's the nitrogen that forms the bond there, so it wants to be NO2. And the complication is that we've got a choice of two spots there, because we know that this one, okay, we've dealt with that one now. Okay, that's spot A, and that's the starting compound, but we've got two other spots to worry about. And the question is, which one does this correspond to? And of course the way we answer that is because it gives us mass spectrometry information. And it tells us that spot B has a molecular ion peak with an MR of 197, whereas spot C has an MR of 179. So we have to just look at this and say, well, does it correspond to either of those? So you just add up the MR of this lot, and you find that it comes to 197. Okay, so the MR is 197. That fits with that being spot B. Okay, so we can say that B is the nitration product that we expected. And again, that was relatively straightforward. So the only really tricky bit is, well, what's going on in C? Because you can see what happens is as a little bit of time passes, we start to make some B. This is spot B. But then as longer time goes, we start to see C as well. So in other words, B is formed first, because we can see that at this point we've got B but no C. But as time goes by, the amount of B decreases again, and we start to get more C. So C is formed by a reaction of this compound. Something else is happening to it over time. So what might that be? Well, the key is really to look at what happens to the MR, and you can see it decreases from 197 to 179, which is a loss of 18. And hopefully that number instantly rings a bell for you and you think, oh, that's water. Okay, when you get a loss of 18, that's very likely to be water. So you look at that molecule and you think, right, how could that lose water? And that should ring a bell, and you think, oh, that's an alcohol, and you can dehydrate alcohols. What are the conditions for dehydration? Concentrated acid. What have you got in the nitrating mixture? Concentrated acid. So that's what's going on here. You're dehydrating that alcohol to form an alkene group here. So compound C is this. Okay, this bit's all the same, but instead of the alcohol you have an alkene group there. The nitro group is still there because that got on there first, but this is the bit that's new. You add up the MR of that, and as we said, you know it comes to 179 because all we've done is taken OH and H away to make a water, and so that's product C. Now that was tricky, that last one. You had to use, bring in a completely different reaction. And there are always going to be a few tricky questions like that, but don't get too hung up on them. If you didn't get that bit but you got the rest of it, you're doing fine. Okay, and that's the end of the test.